Okay, good afternoon and welcome to our webinar on practical guidelines for in vivo dosimetry. My name is Brian Muir. I'm a researcher at National Research Council of Canada, and I'll be moderating this session. This webinar was organized by the APM Working Group on radiation dosimetry. I'm the chair of that working group, and two of our speakers in this webinar, Dr. Patricia Oliver and Dr. Gary Lim, are members of the WGRD. We also have four other expert speakers on this topic in this webinar. We partly organized this webinar in response to the Landauer OSLD recall. The recall notice was issued in July 2023 because it was found that some of the dosimeters did not meet the accuracy specifications of ±5%. There are other OSLD manufacturers, so this webinar still discusses the use of OSLDs as well as possible reuse of the dosimeters. We also give other options for in vivo dosimetry, including TLDs, EPIDs, scintillators, reusing OSLDs, etc. We have 6 speakers. Each of them will present for 15 minutes, and then to close the session, we'll have a half-hour panel-type discussion period where all speakers will answer questions. So, there was just a message in the chat to use the Q&A feature at the bottom of the screen to submit questions, which we'll answer at the end of this. Okay, so our first speaker is Dr. Patricia Oliver from Nova Scotia Health, who will give us an introduction to in vivo dosimetry. So take it away, Patty.
Thank you, Brian, for that introduction. I have no conflicts of interest to declare. So as Brian mentioned, we decided to organize this webinar in light of this recent OSLD recall from Landauer, which I think prompted many physicists in the clinic to look into implementing other alternative technologies. So in vivo dosimetry is a tool that can be used to ensure that the treatment was delivered as intended. And the actual dose to the patient may differ from what was planned due to a variety of different sources of error. For example, patient positioning changes, treatment delivery errors, treatment planning system errors and limitations, and also data transfer errors between the planning and delivery systems. And importantly, other forms of pre-treatment QA cannot necessarily catch all of the errors that can potentially be detected with in vivo dosimetry. So, for example, pre-treatment measurement-based QA could catch some TPS errors, but only insofar as they don't involve the patient's anatomy. In the case of newly implemented technologies, we don't have a long track record of successful treatments to give us confidence that the treatment is necessarily being delivered as intended. With highly conformal hypofractionated treatments in particular, the consequences of a positioning error are potentially severe. So it would be nice if we could do in vivo dosimetry to make sure that the treatment is being delivered as intended. However, there is high uncertainty associated with point detector measurements in regions of high dose gradient. I don't believe that this is relevant for North America, but in some countries it is a legal requirement. And also in vivo dosimetry can potentially be used to observe trends and systematic errors across large patient cohorts. So for example, these histograms are showing in vivo dosimetry results showing the effect of implementing some change in clinical protocol with the solid line corresponding to the post-implementation period. So it would allow you to, this sort of analysis would allow you to identify trends that wouldn't be obvious from looking at a single patient result due to the associated uncertainty. Some authors believe and have commented that all treatments should be verified with in vivo dose measurements. Although it is true that the resources required to do this would represent a significant barrier for many clinics in terms of the monetary costs and staffing time that would be required. In this commentary by Williams and McKenzie, they argue that in vivo dosimetry can prevent those rare catastrophic overdose events. And those events, in addition to being very harmful for the patient, are also severely detrimental to public confidence in radiation therapy. So they're making the argument that it's a question of public perception. In vivo dosimetry is particularly useful for out-of-field doses because treatment planning systems are typically not accurate there. They're not designed or commissioned to be accurate out of field in most cases. This topic is covered in detail in APM's TG158 report. Out of field dosimetry presents several challenges. For example, neutrons may represent a non-negligible contribution to the overall dose, and some dosimeters will over-respond and some will under-respond to neutrons. The spectrum out of field is softer than what's in the in-field region, so detectors with relatively high effective atomic numbers may over-respond if calibrated in the primary beam. Out-of-field dosimetry is especially relevant for implanted devices such as cardiac pacemakers and defibrillators, and also for pregnant patients. So both of these represent cases where there may be adverse effects associated with relatively low doses of radiation. And so accurate knowledge of out-of-field dose would be essential in those cases. TG203 covers cardiac devices, and TG36, which is a relatively old report now, covers fetal dose, and an update to that is in the works. So I just wanted to highlight this case study looking at a pregnant patient with a brain tumor. I think this case study highlights some of the in vivo dosimetry issues associated with neutron dose. So in this case study, they were deciding between treating the patient with either photons or protons. And so they carried out pre-treatment phantom-based measurements. And based on those measurements, they decided to go with protons because it resulted in a lower fetal dose estimate. And then in vivo, they measured neutron dose using these NuTrack detectors, which have a limitation that they can only measure up to 40 MeV. But they're treating with 120 MeV protons, so these may not be able to capture the full neutron spectrum. To get around this limitation, what they did is they examined the relevant neutron fluence spectrum and observed that the peak fluence was approximately 10 times that near 40. And so then they applied this 10 times correction factor to their NuTrack readings, and they chose that factor to be conservative. They then verified this NuTrack correction factor based approach in their phantom measurements, where they were able to measure neutron dose using the full neutron spectrum with a detector that was too bulky to be used in vivo. So for implanted devices, cardiac devices in particular are covered in TG203, as I mentioned, which recommends using in vivo dosimetry if the device is between 3 and 10 centimeters from the field edge. The idea here being that within 3 centimeters, the TPS is sufficiently reliable, and beyond 10, the dose is negligible. TG203 also recommends reporting dose to water, not dose to device. So high Z dosimeters should be avoided, again, because these devices are typically in the out of field region where the spectrum is softer, so they might over-respond. This is also relevant for capturing the IGRT dose component, which is typically due to low energy photons. In terms of the depth, ideally, the depth of the implant is matched with the depth of the dosimeter in terms of the water equivalent depth of measurement. This is important because in the out of field region for MV photons, the surface dose is actually enhanced due to contaminant electrons. So you actually see a build down effect near the surface out of field. And so for this region, TG203 recommends adding a bolus to match the depths. Now I'll move on to a case where we were looking at in vivo dosimetry in the field now. We were considering various options for bolus in chest wall radiotherapy. So we did some preliminary work with phantom measurements and Monte Carlo simulations to help the radiation oncologist decide which bolus type and usage schedule they wanted. And then eventually we moved on to in vivo measurements on real patients. And one of the first things we noticed was that our no bolus in vivo measurements were higher than what we had expected based on our preliminary work. And this turns out to have been because on real patients, they had gowns and blankets on top of their skin and on top of the dosimeters. And so this was causing buildup and dose enhancement. So that was a bit of a troubling find before we realized what was going on there. Skin dosimetry in general is particularly challenging because it's at the surface where there's a high dose gradient, unless, of course, there's bolus. And many treatment planning system dose calculation algorithms are not accurate within the first millimeter or so. Per the ICRP, 70 microns is often considered the relevant depth for skin dose. However, it is important to note that the skin thickness does vary throughout the body. And in breast radiation therapy, an area effect has been noted. So the probability of skin toxicity has been shown to be dependent on areas greater than 1 centimeter squared receiving considerable dose. So anyway, if you were interested in getting dose at 70 microns depth, then you can get this from Monte Carlo simulations or extrapolation chamber measurements. And then those results can be used to determine correction factors for other detectors that can be used in vivo that have differing water equivalent depths. So in terms of emerging techniques in vivo dosimetry, the group led by Dr. Brian Pogue have developed a system that takes advantage of the observation that Cherenkov light intensity is proportional to surface dose. So here are some examples showing some issues that were detected using their Cherenkov system in cases where the image guidance and the surface guidance were within tolerance. They were showing that the patient setup was within tolerance. So, for example, showing that the contralateral leg is spared, um, monitoring dose spill onto a patient chin, bolus placement, and MLC leaf placement errors were identified. Dr. Tala Monogemi's group have developed 3D printed scintillator arrays that are designed to conform closely to the patient's skin surface, and the light that is emitted by these devices is detected by a stereoscopic camera pair. And then with appropriate calibration, this can be related to dose. In terms of proton therapy, on-the-fly reconstruction of induced PET activity maps has been demonstrated. There's also prompt gamma ray imaging, where it's the gammas that are released as a result of de-excitation of tissue nuclei that are detected. And if the gamma camera is placed orthogonal to the beam, then this can be used for range verification. So with both of these technologies, the question is how exactly does the signal relate to dose? So these are areas of ongoing research, but the positional information that they provide is nonetheless useful. And one last thing I wanted to mention is interpreting results and deciding when to take action. Here's one example where the authors delivered test plans with and without intentional errors added in. And this allowed them to then calculate true and false positive fractions for a range of different tolerance values, where here tolerance value refers to their gamma pass rate threshold. And then the optimal tolerance was selected as being the point closest to 0 false positives and 100% true positives, so as close as possible to the upper left corner. And then each of these different curves is for different gamma criteria. So this is for an epid transit dosimetry system, so a 2D system. And also it's important to be aware of the expected reproducibility and uncertainty associated with the in vivo dosimeter that you're using. So here's a really useful table from a review paper, which I have the citation down in the corner here, and I just wanted to point this out as being a really useful reference, really useful resource. So thank you. I'll stop there.
Okay, great. Thanks, Patty. Okay, so for anyone who missed the introduction, we'll go on, have all the speakers present first, and then we have a 30-minute question and answer period at the end. Our next speaker is Paula Alvarez from the University of Texas MD Anderson Cancer Center. Paula is a medical physicist at IROC Houston and helps lead IROC's TLD and OSLD dosimetry systems for remote radiotherapy audits. So go ahead, Paula, whenever you're ready.
Thank you, Brian, for the introduction, and thank you, everybody, for joining this webinar. So I'm going to be presented the use of the nanodot from Landauer at IROC Houston and guidelines provided by Task Group 191. Just remind that IROC is based on an NIH grant. So when we talk about the nanodot system, I would like to make a distinction between two parts of that. The first one is the nanodot as a detector. This detector has a shape of a 4 millimeters diameter disc, 0.2 millimeters in thickness. The material that is the OSL material is aluminum oxide, and the whole detector is mounted in a plastic cassette of 10 by 10 by 2 millimeters. So it's very suitable regarding dimensions for in vivo dosimetry. And in our case, because it can store without very complications the dose, it has been very useful for external audit. Based on datasheet from vendor, you can see here the range in energy as well as the range in dose. Our experience has been using photons, electrons, HDR, and we also have a fully commissioned but never implemented for proton system. The second part of the system is the reader per se. So there are two models that they were able to read nanodots. The first one is the MicroStar model, which is the dark blue reader on top of the image, and MicroStar 2, which is the latest one, which is on the bottom. The reading engine on these two readers is based on an LAD plus a photomultiplier, and each one of these readers has a dedicated software to take readings and process dose calculation. But I would like to make the comment that these two readers are not compatible. The reading engine is completely different from one to the other, making these two systems not equivalent. So calibration from one cannot be transferred to the other reader. The way to run calculation of those is following Task Group 191. So the equation for those looks like a TG51 equation. You're required to look for a corrected reading, have the calibration of the system, which is labeled as NDW, and then a series of correction factors that are going to be, those are how the commissioning needs to be done. So there's going to have a lot of information is the assumptions you're making on the system and how you define your geometry in order to have these correction factors defined. With that said, and based on the assumptions you might be making or how you define this correction factor, Task Group 191 proposed 4 different levels in the final uncertainty for those calculations. IROC has what is called high accuracy and control scenario that is able to provide a final uncertainty in dose at the level of 3.2% at 2 sigma. So important things regarding getting this uncertainty and this control scenario is coming in the way that the correcting reading is calculated. So this is, again, equation coming from 191. This correcting reading requires the knowledge of a background. In case on the IROC system and based on the reading we were using, background is negligible. The OSLD system gives you the possibility to take multiple readings, and so the final correcting reading is going to be coming from an average of readings. The reading engine is the same type of process that is required to remove signal, so a depletion correction needs to be taken into account. Both readers shows to be negligible, but you can take that correction also there. But the most important thing here is the individual calibration of the KSI value. These detectors requires the identification of individual calibration to process that information. So I would like to mention the work published by Hayden Scott early this year, and two analyses were done coming from this paper. The first one is the consistency of the KSI based on accumulated dose. So what he did is irradiate, process KSI, bleach the system, go back to the original signal, and keep processing KSI. And what he showed is that the KSI values, the distribution of them show consistency up to an accumulated 48 gray, close to 50 gray. The second parameter is the performance of the system. Task Group 191 suggests that you can reuse them without any change in the performance up to 10 gray. Vendors suggest not reuse, but in this case, Scott looked into the performance and was able to find consistency up to 23 gray accumulated dose. So this gives the room to actually reuse the system on a safe way. So let me show what actually type of QA we are doing in IROC. We already went through more than 6 batches of OSLDs. And what I'm showing here is the distribution of KSI for our last batch, which is labeled 20K21. This batch has more than 17,000 detectors calibrated. Our detectors are under the condition on unscreened detector. The KSI accepted values is from 0.94 to 106. The commissioning is done in group of 100 at the level of 1 centigrade dose level. The commissioning is done whenever 500 detectors are commissioned, a re-verification of the KSI is done on a group of 125. So what you can see in the graph here of G185 is a comparison of KSI coming from the QA of the commissioning, and you can see that all the KSIs are within a criteria of 1.5% or less. Part of that QA is also consistency on the reader. Our system was developed based on 4 readers. And you can see on the bottom graph is the consistency of the KSI over the use of the different reader. And again, a criteria of 1.5% was applied there, beating that requirement. The other important point is a consistency on the program. So what I'm showing here is the histogram of the results coming from our output check program based on OSLDs. We moved to OSLDs in 2011. All the results, which were more than 16,000 beam check, show a particular distribution that is consistent even when we look at the distribution coming from 2019 on 2023, which is the latest one. We are reaching right now close to 20,000 beams per year. The histograms are basically the same. Values are basically the same. And I want to show that over this lifetime, we have 6 batches and 2 models of readers used for this program. And this type of histogram is exactly the same type of histogram we used to have before 2011, which was the time we were doing, only TLDs. So what we have right now with nanodots. So there are legal implications because of the recall letter that Brian mentioned in the beginning. Recall letter was not only issued for nanodot, but also for the readers. So it's important to have discussion with the legal team at your institution to explain the use of these detectors. In our case, we have considerations regarding the implication of the recall letters. And one of the important things that we found is the support coming from peer-reviewed documentation, and Task Group 181 is one of the biggest documents we use in the support of the program. But the biggest limitation we have right now is that the product was completely removed from the market and there is zero support from the vendor. Thank you very much.
Hey, great. Thanks, Paula. Okay, so our next speaker is Dr. Wesley Culberson from the University of Wisconsin-Madison. Wes is the director of the UW ADCL and oversees the UW Therapy Dose Verification TLD service. So Wes will be talking about TLDs as in vivo dosimeters. Take it away, Wes.
Thanks, Brian. Can you see my screen okay, Brian?
Yep, all good.
Okay, wonderful. Yeah, thanks for the introduction. My name is Wes Culberson, and I'm the director of the UW ADCL, but today I'm actually going to be talking about a different role that I have just within the lab. We have a TLD in vivo dosimetry program, and that's what I'm going to be talking about today. This is a talk geared both towards physicists that might want to start an in-house TLD in vivo program, or if you would choose to do a remote service. The information that I'm going to talk about today should cover both of those. I don't have any conflicts of interest. I am going to show some products in this presentation, but I don't endorse them. And I'm employed by UW, where we offer these services, but I don't have any financial incentives if you choose to go with them. So we need to start with some basics of TLD physics, and these physical parameters will apply whether you do it in-house or with a remote service. They are, TLD stands for thermoluminescent dosimeters. They're solid state detectors, and they store energy by electrons in various trapping levels. The material itself is an insulator. It's not a conductor, not a semiconductor. And the electrons release energy after they're heated, and they recombine with the holes in the recombination centers where there are impurities. The light is emitted when the TLD is heated, and then you quantify that light. There's a lot of varieties of TLDs out there, lots of formulations and base materials. Today, I'm really going to be concentrating on one formulation, lithium fluoride, with the impurities of magnesium titanium. That has a brand name called TLD 100 because it's the most common for in vivo dosimetry. It has an effective atomic number of 8.4, which is really nice. It's very similar to tissue at 8.2. That's one of the benefits. So this slide, I'm going to go through some advantages and disadvantages of using TLDs for in vivo dosimetry. An advantage is the density is 3 orders of magnitude higher than air. So it's a whole lot better than an ion chamber for this type of dosimetry. And because it has a high density, it has a very high spatial resolution. You can get TLDs that are very, very small. In fact, probably smaller than you want to work with. So you choose sort of a medium-sized TLD for in vivo dosimetry. They're cheap to manufacture and a relatively cheap solution overall compared to other services. They don't require power supplies, cables, or any additional batteries or power. They're unidirectional, so they don't really have any angular dependence. They're dose rate independent. In fact, there's been some studies lately showing that they are good with flash energies or flash dose rates. They're resilient to fluctuating temperatures. In fact, we've known some TLDs to go through the washing machine and they come out and are still accurate. I'm not encouraging that, but they are pretty resilient to the temperatures. And they're accurate over a very wide range of doses. They go down to microgray, which is really low. They're also accurate up to kilogray. So what are the disadvantages? Well, they do have an intricate dependence on energy, especially down in the low kV range. They are superlinear above 8 gray. I'm going to talk a little bit about both of those things. You can't get a direct ADCL calibration available. That's the case at any ADCLs and most of the detectors we're talking about today. They can be susceptible to surface contamination, especially from nitrogen gas and some of the readers. You can damage them if you're using tweezers or other holders that can damage the surface of them. And you have to wait 24 hours to read them out. So they're a passive detector. The readers, there are a variety of readers on the market. This is a common one if you have a pretty big TLD program that you operate. It's called a Model 5500 from Harshal. It has a carousel that rotates around and it can hold up to 50 TLDs and read out all of them in one automated session by heating them with nitrogen gas, lifting them up in the air, and the light is recorded on a photomultiplier tube. It's a very nice system. It's very efficient. There's also a single TLD reader, which is what a lot of hospitals have. Some older ones are around still. This one's called a Model 3500, where the TLD is placed on a planchette or a little hot plate, and that hot plate is heated up and a photomultiplier tube reads out the light. The readout process itself involves a glow curve. This is an example of a glow curve for a TLD 100 material. And here you can see the various peaks. As the temperatures increased and the TLD is heated up, there are different trap levels that are released. So you see these different peak intensities. And those, in theory, can be deconvolved to see the individual impurity peaks within that glow curve. But in reality, we typically like to heat them up a little faster. This is a glow curve from a 5500 reader, one of the automated readers, where the red line shows the increase in temperature or heat versus time. And then the big blue area is the area under the curve. And you can see you can't even distinguish the peaks on this glow curve, but that's okay because it's a total integrated area under the curve that's used for the TLD reading. Handling TLDs is a little tricky. I recommend if you get into this program to use vacuum tweezers. You can see a photograph on the right of a vacuum tweezer. It's just connected to like an aquarium pump. It's pretty labor intensive. The chips can affect the reading. Chips in the TLD can affect the reading. And microcubes are very difficult to handle. So I would recommend not using those. But here's a photograph on the bottom showing some microcube TLDs, how small they are. When you choose to use TLDs, you can either keep track of their individual sensitivities, or you can use what's called batch sorting. And that's when you take a very large batch of TLDs. On the bottom right, there's a photograph of a holder that holds 1,000 TLDs. And we could take that holder in front of a cobalt-60 source or cesium source or whatever and irradiate all of them at once. And then after they're all irradiated, you read them out and you get a sensitivity. We typically like to perform this 3 times to get an average sensitivity of each TLD. And then what you can do is bin those sensitivities into bins that are about 1.5% in agreement with each other. And then you have a whole group, and it's called sorting TLD. So I've got a little Harry Potter sorting hat over there. And once you have them sorted, then what that means is you don't have to actually keep track of each individual TLD, because it's very hard to write a number or a QR code or keep track of them in any way. So it's nice to keep them in just groups by sorting them. After you've sorted them and irradiated them, then you have to anneal them. That involves an oven or a furnace. First, you need to reset the traps at 400 degrees C for an hour. Then we like to heat them lower and slower for another 24 hours to remove some of those low energy traps that makes the readings more accurate later. And then cooling actually has a large effect on the TLDs. We like to put them on aluminum plate at room temperature. I mentioned earlier, TLDs are super linear. So they are linear up to about 8 to 10 gray. For TLD 100, they go super linear at 10 gray. Up to a kilogray, you can see on the right the sensitivity or the calibration as a function of exposure or dose. And you can see it starts to bump up and deviate from linearity. After a kilogray, they do start to experience some damage, although there are some people that are able to manage that. And typically we like to use them up to 10 gray for in vivo dosimetry. The calibration of a TLD is typically done against a reference class ion chamber. You could use a variety of beam qualities. You need to calibrate within a dose range that's appropriate for your expected use. So in the linear range, for example, if you are expecting a result around 2 gray for like a typical treatment, fractionated treatment, then you'd want to calibrate at 100 centigrade, 200 centigrade, and 300 centigrade, create a response curve. You can actually extrapolate down to lower doses pretty easily. We do that with our services, if they get a really low dose, but not really to higher doses very easily because of the superlinearity. So this is just a picture of one of our forms where someone is irradiating a low, a medium, and a high TLD, and you send these in along with the control TLDs. You need to pay attention to the location of the calibration. So the entrance dose versus the ion chamber depth. And you don't necessarily want to just place the TLDs right on the entrance if you've determined the dose at Dmax or a deeper depth. So you'd like to keep those two consistent when you irradiate your calibration TLDs. The precisions of TLDs can be very good. If you have a proper handling and robust, repeatable system, they can be as low as 2 to 3%, and that's with a 95% confidence level. For in vivo measurements, there's a lot of additional uncertainties, such as the gradients on the skin, if you have a cone beam CT, things like that. So overall, the uncertainty of the whole procedure is about 5%, can be greater. But really the TLDs themselves are pretty low uncertainty. The service we offer, I'm showing, this is our A2LA scope of accreditation, showing a 3.6% uncertainty is what we quote at a 95% confidence level. And if you use 3 TLDs at each location, that can help approximate the true value better. The response of the TLDs is usually pretty good in the megavoltage range. So if you calibrate them at cobalt 60 and you irradiate with a linear accelerator, it's a pretty small change in response. But for low energies, so if you're using this in a kV orthovoltage type system, they do over respond. And this is a plot from, this is figure 3 from Nunn et al. From 2008, showing the measured TLD 100 energy response to the kV region and showing the increase of about 40%. So you do have to keep that in mind if you're irradiating to the low kV energies. To do the in vivo dosimetry itself, they need to be protected from the bodily fluids. So showing here some small baggies that can be placed on the patient. You can just heat seal these baggies pretty easily. Typically our program, you need to calibrate on the beam that you're using them for. That's the most accurate way to use TLDs, and also to use a control TLD. So on the bottom photograph, you can see what we would send out. Those would normally be cut up for a low, medium, and high dose and a control set of TLDs. The applications for in vivo dosimetry, there's pretty wide range of applications possible. You can tape them onto the skin. You can put them under bolus, which is recommended for that equilibrium. The breast is the highest percentage of uses that we see from the service at UW. Pacemakers, some tricky IMRT plans for electron treatments. You can put them under some bolus or right on the skin. For total body irradiation, it's pretty easy to put 5 TLDs on. Pregnant patients, that was talked about earlier, and some other special procedures. Now, I mentioned that imaging dose. So if you choose to do a cone beam, which is what a lot of people do before treatment, and the best thing you can do is to somehow place the TLDs after the cone beam. That'd give you the most accurate result. But oftentimes the reason you're doing the cone beam is because you've got a setup that's a bit intricate. So oftentimes the TLDs are placed on before you leave the room and do the cone beam. Just knowing that you get an over response of about 40%. I have a graduate student, Andrew White, and we have a publication where we're going to be reporting dose values for a variety of imaging protocols, the most common ones for both variant and Elekta systems. But the results are that it's about 0.1 to 5 centigrade. And so you in the meantime, until that publication is out, you have to use your best judgment and subtract a little bit of dose. The results, the Australian group has a nice publication on TLDs that they've used for 5 different campuses and a very large therapy group. They did 310 measurements over 2 years. And table 1 in their paper shows the results. They found less than 1% major discrepancies in these treatments. One of those actual errors led to purchasing some new software. About 8% of the cases saw disagreement that was greater than 5%, but not quite actionable. And so if you're interested in this group, and they did a lot of analyses in this group, this publication is very good. You can expect some discrepancies, right? If TLDs are placed directly on the skin, surface dose is very difficult to predict, even with modern treatment planning systems. So I would recommend putting these under bolus, even if it's just a little square bolus, maybe a couple centimeters by a couple centimeters. It's just the first day, doesn't really affect the treatment dose over many fractions. And that's not always an option, but that's the preference. And because there's this charge particle disequilibrium at the surface, it makes it difficult to interpret the results. The cost of TLD dosimetry, the Australian group actually has this in their publication where they list some of the costs. If you choose to get an automated reader and try to do this for a pretty large group, it turns out it costs about 200 Australian dollars per measurement. That's mostly because the readers are pretty expensive to buy and to maintain. They can be a bit labor intensive, so you have to have some people doing the work. And you can also choose to do a mail order service like the one we have at UW. And for this, the prices are $100 or $125 for 5 TLDs. So I believe this brings me to the end of my session. And if you have any questions, you could type them in the chat. And I do have one great article here with additional references. And I believe this might be the same one Paula showed earlier. It has a lot of information on TLD dosimetry. So thank you for organizing, Brian. I think this is a nice webinar trying to meet a need. And I'll pass the mic.
Great. Thanks, Wes. Okay, so our next speaker is Dr. Gary Lim from the Memorial Sloan Kettering Cancer Center. Gary is a member of the APMWG-RD, the Working Group on Radiation Dosimetry, which organized this webinar. Today, Gary will be talking about the use of radiochromic film for in vivo dosimetry. So go ahead, Gary.
Thank you, Brian. Thank you everyone to join this webinar. And this is my disclosure. This is the outline I plan to talk about today. So just when we start, I just want to have some fun fact. And radiochromic films are initially developed by the company called GALF. And I think that name kind of stuck with us. Sometimes we call it galvachromic film or radiochromic film. They really mean the same thing. So it is a relative dosimeter. The active ingredient on the film is a radiosensitive monomer. So when it got exposed to radiation, it would turn blue, starting what we call the polymerization process. As you can see on this plot, on the solid line here, is the unexposed absorbance of the films when it gets scanned into a scanner. If we expose it to, like, say, a 500 centigrade radiation, the shape of the curve would change, and it turning blue, meaning that it will absorb red and green colors, as shown here. So these two peaks represent the high absorbance of the film and the reason of being turning blue. And this polymerization process is the fastest, within the first 24 hours. Unlike the radiographic films, the development or developing films is not required for radiochromic film. And currently, there are several different types of films available for different applications, from diagnostic to radiation therapy. But today, we're really going to focus on the films for radiation therapy, and they typically range from 0.01 to 1,000 gray, and they have thickness vary from 109 to 278 micron, and they all typically considered to be tissue equivalent. So film has been used quite extensively on several applications in vivo dosimetry. And I think Patty also mentioned some of that in her talk earlier on. So here is a intraoperative electron radiation therapy. And films was used to, for example, this is a breast treatment with the shielding behind the soft tissue. Films are being used to verify the position and for dose verification. In here, you can see the films on the left here is really putting in the actually the superior part of the shielding to identify the positioning, and you can see that it was actually missed a little bit and used for position verification. And the film on the right is placed behind the shield to ensure the dosimetry is acceptable and the shield is being effective for shooting the radiation. And for external beam radiation therapy, typically is placed on skin under some bolus to really improve the that Wesley already mentioned, to give better build-up region, to get better dose, reduce the dose uncertainty. And typically is used for dose profile, dose verification, and for some special treatment like TSEB, TBI, superficial RMRT. Here on the left here, it's a case where we use films for electron treatment under bolus. And here is a shown on the left. On the right here is a shown for small film being cut up, placed on the patients to measure the TSEB. So films can be used for a single point measurement, or you can use for 2D dose distribution, depending exactly how you cut them up. So I'm just going to talk briefly on the characteristics of films here. This is from TG235. And films can be categorized into 3 types: type 1, type 2, type 3. And you can see that the yellow here is the active layer. In type 1, the active layer is on the front with a substrate or some kind of polymer bonded behind it. And type 2, this is typically what we've seen in the earlier type EBT2 films, where you have asymmetric bonding on one side of the film versus the other. And type 3 is a symmetrical bonding with sandwich with active layer right in the middle. Here are the current radiotherapy class graphcomic films in the market. They're EBT4, EBT3, XD, V3, and V2 films. Typically, we'll be interested in the EBT3 or EBT4 films because of the higher sensitivity for in vivo dosimetry. Looking into EBT3 and EBT4, what are the differences? There are some physical differences. Here in EBT3, the polymer that bonding or sandwich the active layer is 100 microns symmetrically on both sides. And when we have the EBT4 here, it's 125 micron on both sides. So it's a little bit thicker than EBT3. And my understanding is the process of making them is slightly different as well. So switching over, or the energy response, which is quite important in understanding the use of the film. Here is the dose response on the y-axis and the dose range in the x-axis. Here, looking for the dose response relative to an ion chamber system at 6 MV, exposing it at different dose range from, I think it's around 50 centigrade to about 1,000 centigrade, and scanning it into 72 DPI and 300 DPI. As you can see, the scanning resolution really doesn't make a huge difference here. So let's just focus on the 72 DPI, which is probably applicable to most applications here. Ranging from energy from 15 MV, 6 MV FFF, and 10 FFF. In the MV region, they're all pretty similar response, meaning that you probably can use a single calibration curve for all the MV beam. But what we notice here in the lower energy, in the superficial orthovoltage range, we do see a significant energy response compared to 6 MV. So what it means is that when we look into the lower energy range, if we want to do in vivo dosimetry, we should consider using a calibration curve in the KV range. And we should not use an MV calibration for that to introduce a systematic error. And on the side, some really our experience in that institution, we found EBT4 to be more consistent in terms of dosimetric response than EBT3. And because of that, we have stopped using EBT3 and completely switched over to EBT4. So let's just switch over to some tips on preparation and the readout system. So before you irradiate film, certainly you want to cut them up and mark the orientation carefully, because films are polarizing, and if we scan them with an orthogonal position, you can introduce a dosimetric error. And you do want to put films in a plastic wrap or bag before you place on patients to reduce any bodily fluid to be placed on it, affecting the readout. When we come to readout systems, there are a single point spot densitometer. And this is an example of that, where you can place a piece of film right in the middle of the reading here and read out the density. But this is only good for single point measurements. So just keep that in mind if you plan to use that. Alternatively, you can use a film scanner. It can be transmission type or reflective type. And here's an example of that, where you can do it can be used for single point or 2D dose distribution. For 2D dose distribution, you really need to also think about correction for the flatbed scanner in terms of uniformity or lateral correction. So when you read out, you should always want to read it out after 16 to 24 hours per radiation. And the reason is, as you've shown here, the y-axis here is a relative reading relative to the 24-hour mark. And the x-axis here showing the post-irradiation. As you can see, within the first 24 hours, it is really growing very rapidly. And beyond 24 hours, it tends to stabilize a lot. So to reduce and then the dose growth is also very different at different dose range. So you want to wait until the curve or the dose growth to be in a stabilized range. And TG235 recommends between 16 to 24 hours post-irradiation. I think that's a good recommendation there. And the next thing is you want to scan them at the same orientation because it's polarizing. And as you can see here, we typically will put a mark when we cut up the film, and when we scan them, we orient them the same way to reduce the polarizing uncertainty. And the last thing is the bit depth. We will recommend at 16 bits if possible. For older scanner, it could be 12 or 8 to 12 bits. But if you can, having a deeper depth of the bit in terms of color resolution, it would be very helpful. Now, when it comes to calibration, it is typically using the dose relationship of net optical density or directly using the intensity. This is a net optical density formulation where the I0 here really is the base fog with no exposure of the film. And in the bottom here is the exposed film density. And you can use a single channel calibration, and we want to calibrate film for each batch of film for consistency, because we will see a batch to batch variation. And here's an example of a single channel calibration. On the y-axis is the net density, optical density, and the x is the dose range. Alternatively, you can also use the multi-channel calibration, and this probably will involve some software, commercial software. There's quite a few software out there, but for those who want to implement that, there are also a paper by Andre Mackey describing the implementation of that. In terms of dose range, you want to clearly have the base fog or 0 dose to a dose beyond your expected maximum dose for the clinical fields. Typically, you want to go at least 10 to 20% so that you ensure your clinical fields fall within your calibration curve. When it comes to in-vivo dosimetry, you want to also have a reference film on the day that you measure your clinical fields. That should be at the same range or around the same dose of your expected dose. And this is really to rescale your calibration film so that your curve will be at the same range or the growth point of your clinical fields to reduce other uncertainty also, such as the machine variation or the scanning variation. Other consideration is the uniformity correction and lateral correction if you're doing the 2D dose profile or 2D dose in-vivo dosimetry. Here's a sample of a clinical in-vivo film dosimetry procedure that we implemented here in our institution. As you can see, it is a pretty complex process that we just described. So having a clear process very helpful in the clinic. For example, we clearly identify that you need to have the same batch, which typically shown on the box of the film that we're being used. So if we don't have a calibration curve, we'll want to generate a curve, and then we'll scan it after 24 hours, and then we'll build the calibration curve, and then we'll convert the film to the dose using the calibration curve. However, if we already have a calibration curve, we will use a one-scan scanning procedure or protocol. And then we'll measure a reference film, as we have mentioned earlier on. And then we'll wait for a time defined by the time difference between the reference field and reference film and the clinical fields. For example, if I measure our in vivo dosimetry at 12 o'clock, and then we measure a reference field at 1 o'clock in the afternoon, so we have a 1 hour separation. We don't want to scan the film at least 4 hours after our reference fields. And once we have that, we then scan that and then follow the same procedure to generate the dose map on the clinical field. The reason, as I mentioned earlier on, to do the reference field is really to rescale a calibration curve to the day of our clinical fields to reduce any uncertainty due to scanning, due to other issues in terms of output or scanning. So when it comes to uncertainty, Devik back in 2005 discussed the scanning process of EBT films. As you can see, for dose beyond 0.4 gray, I think it's very well under control to within 2%. So this applies to most in-field in vivo dosimetry. However, for dose less than 0.4 gray, the lower the dose has a higher dosimetric uncertainty. It is challenging for cases such as, our field dose. So I think this is some place where each clinic will have to assess that acceptable uncertainties and assess whether or not film can be used in this application. In our institution, for example, we assessed that and we found that it is too high of an uncertainty. We do not use that for our field or low dose application. So in conclusion, we think that EBT film certainly can be used for in vivo dosimetry, and it can be used for 1D or 2D in vivo dosimeter. For energy range above MV, it can be considered energy independent. Uncertainty is well controlled for dose higher than 0.4 gray, and I think I will recommend establish a very clear clinical process if we want to use in vivo dosimetry, simply because it is a complex process, unlike the OSLD system that we've been using it clinically. So to that, I conclude my presentation.
Hey, great. Thanks, Gary. Okay, so our next speaker is Dr. Kyle Paget from the University of Miami School of Medicine. Kyle was a member and author of the AAPM report number 307 on the use of EPIDs for patient-specific IMRT and VMAT QA. Today, he will talk about the use of EPIDs for in vivo dosimetry. So go ahead, Kyle.
Let me start that over. I was muted. Good morning or afternoon, everybody. My name is Kyle Paget. I'm going to talk about in vivo dosimetry using EPID technology. And at the end, I'm going to give some guidance from our recently published task group report. So the previous speakers have already done a really good job of giving the motivation for in vivo dosimetry in general, and the same rationale exists for transit dosimetry. So why is EPID a good choice for these measurements? So EPID has a lot of advantages. It's non-invasive, so it's attached to your LINAC. It just retracts out of the machine and positions itself behind the patient. You don't have to attach any additional devices or monitoring cables or anything to the patient, so it's convenient in that way. It's electronic and it's attached to your machine, and it's attached to the record and verify system. So as you collect the data, it comes into your system in essentially real time. Another huge advantage of EPIDs is its size and resolution. So again, it's relatively large and it's positioned behind the patient. And so you can essentially capture the entire two-dimensional dose distribution as it exits the patient, right? And so that can be used for two-dimensional analysis. And then if you collect these two-dimensional fields at every beam angle, you can use techniques to reconstruct the dose in 3 dimensions and doing even more powerful analyses with that. So a quick review of the different flavors of transit dosimetry using an EPID, starting from the least complicated to the most complicated. 0D is where we utilize the EPID to make a point measurement in the patient. 1D is where we utilize the EPID to make a So you will capture the exiting dose from the patient, and then you will reconstruct that dose back at a single point. That's typically done at isocenter, but can also be done at other locations. Is then not overly complicated. It can be a very efficient tool for tracking basic fractional dose delivered. I think this satisfies some of the requirements that maybe our European colleagues have for tracking dose for each fraction. 2D transit dosimetry, again, one step up in complexity. You capture that two-dimensional dose distribution across the entire field, and then you can use that in either relative mode or absolute mode to verify the dose pattern for that fraction, and you can compare it to expectations from the TPS, or you can track trends with it as each fraction is delivered. You can look at that two-dimensional pattern over time. 3D is one step up again, where we're collecting all the two-dimensional dose distributions from all the beam angles, whether they be VMAT with rotational gantries or static IMRT. And then we use techniques to reconstruct the dose back into the patient frame of reference, either the planning CT or the daily cone. And this provides more insight into the actual clinical impact of different errors or dose distributions from changes in the patient or the treatment. And finally, the DVH analysis. This is the most powerful and sometimes the most impactful method for looking at in vivo dosimetry with an EPID. It relies on a 3D reconstruction of the dose as well, but it also does automatic contouring to give us a DVH and some dose metrics. And we can very easily translate these impacts, the clinical impact of any deviations we're getting. Kind of rehashing a lot of that in now a table form. We have 0 to 3D over to DVH, so complexity. You can see it's increasing over here, and you can see that the DVH and the 3D, they have the most uncertainty with them. They take they're most complicated. They take more assumptions into play, and so when we recommend at the end the different tolerances and the amount of integrity that these solutions have, you have to take that with a grain of salt because they have many step process to get to their final result. But they do have maybe the most minutia of detail about what's going on inside the patient. Whereas the 0 and the 2D transit is a little bit easier, a little bit more robust, but maybe a little bit less on the information that it provides. So quickly looking at some of the techniques that are used to make these two-dimensional comparisons. So again, the EPID is used to calculate to measure the exiting radiation from the patient. Often relative assessments are made. So this is where the EPID image collected on a daily fraction is then compared either to a reference image. So call that a fraction 1 image. So you can look at how everything's changing compared to fraction 1. Or you can compare it to like a predicted image from the TPS. So you can see what the response is as compared to what you expected from your original plan. These are powerful, right? You can identify treatment variations, and you can also identify trends, certain things like patient weight loss or systematic displacement of the patient. These are things that you can monitor with these techniques. But the problem is that some of the deviations, errors that you do detect, it can be difficult to correlate back to three-dimensional dose distribution. So while you'll notice things changing, and that might trigger a further investigation, you might not be able to say, oh, I can see that the dose to my OAR or my target are specifically impacted. So three-dimensional dose, going through that same process. So again, we're collecting the data as it exits the patient with the EPID. And then we're typically using back projection methods to reconstruct that dose back into the patient frame of reference. So it's either the planning CT or the cone beam. And so now you have a 3D dose distribution inside the patient, and you can compare that 3D dose distribution back to the original TPS distribution. So you can look for changes, and you start to see where inside the body these changes are occurring. So again, these dose differences are easier to evaluate than two-dimensional comparisons. But again, correlating gamma passing rates or failure rates to specific dose errors can be challenging. And again, 3D dose calculations using EPIDs and transit dosimetry, they suffer from some uncertainty due to a lot of the assumptions that have to happen to make that measurement calculation. Here's a quick example that we published in our TG 307. This example is nice because it gives both 0D and 2D examples in one figure. We're collecting a point dose at essentially ISO center. It's like not a point dose, but it's a 9x9 pixel grid. So a real small area right in the center. And that uses absolute dose calculation using back projection methods. So we're just calculating an absolute dose in one position, but we're using relative 2D transit dosimetry to evaluate trends over time. So you can see up here in this corner, you have the EPID response for a fraction delivered on December 5th, and then another fraction delivered on December 9th. And then it's giving you a gamma analysis between those two assessments. So you can track changes over time. And for head and neck, as in this example, it could be tumor shrinkage, or it could be weight loss. Things like that are easily detected with these methods. Trying to give an example of DVH comparisons. These are much easier to interpret the clinical impact of any deviations you're tracking over the treatment course. Here in this example, this is a DVH showing, and the solid line is showing the treatment planning DVH, and for both the PTV60 and the parotid, and then also shown is the fraction 15 DVH. Maybe a bit of an exaggerated DVH comparison just for effect, but just visually, you can see the impact to both your target and one of your important OARs from deviations on an individual fraction. You can also do automated analysis and scripting analysis of these kind of DVHs. So this is another one showing the treatment plan analysis for certain key OARs and some targets. And then you can see here what happened on fraction 15, that left parotid and that target are now failing. So it's a nice way to generate automatic reports, and it's easy to script and alert you when things are going maybe sideways in your treatment. But it does suffer from certain uncertainties, right? So your cone beam is not a planning CT, so it might not have sufficient field of view. The algorithms that are used to correct for the uncertain Hounsfield units of cone beam aren't perfect, and so you might not get perfect HU correspondence on your data set. And then obviously the contouring accuracy. These tools have contouring that's automatic, and that's great and all, and they're improving over time, but they're not perfect. All right, now a little bit of some of the errors that you can detect using in vivo dosimetry, and I'm sure these are also applicable to a lot of the in vivo dosimetry methods that have been presented so far. But for non-transit dosimetry, this is our pretreatment IMR-TQA as a reference, things like portal dosimetry or ARC check. These techniques are really good at detecting errors in your planning or your treatment delivery. So like MU errors or MLC positioning errors or gantry or collimator errors, things like that. Well, transit dosimetry can also detect these errors, maybe with a different amount of sensitivity, but it also is designed to identify errors, and specifically in dose delivery, patient positioning, and anatomical changes. So this is a table from our task group report, and these are some of the errors that have been published about and using EPID transit dosimetry. You can see the plan-related stuff, kind of like similar to the IMR-TQA, patient-specific IMR-TQA. A lot of patient anatomy things. So the lungs filling with fluid, the patient gaining weight, the patient losing weight, bowel gas changes, weight loss, bladder filling. These are some of the things that people have been able to detect using these techniques. And also patient-related delivery errors. So wrong patient positioning, wrong set of immobilization equipment, just things like that. So these are some of the common errors that EPIDs are good at detecting. So quick overview of what the task group covered. So it covered both pre-treatment QA as well as transit dosimetry with EPIDs. Obviously, I'm not going to talk about the pre-treatment QA stuff here, but we wanted to give a full overview of the clinical applications and limitations of these products. We wanted to give a review and assessment of the different solutions that were currently out at the time of publication. Recommend a lot of QA tests and ways to commission and implement these solutions in your clinic, and then also provide recommendations like tolerances and action items for when you do detect changes. These are kind of the rest of the talk. I'm going to look at some of these topics here. So error detection sensitivity. This is important. It's probably important for every single in vivo dosimetry technique that's out there. It's important to understand what level of error that you can detect with your system. And so one aspect of the task group report is where we recommend you take existing plans and you introduce known errors to it of different magnitudes, and things like MLC positioning or patient thickness changes. You can step up the amount of induced error, and then you can start to dial in exactly how sensitive your software solution, your EPID solution is at picking up on these issues. It's a really complicated topic, so it's all in the task group report if you want to read more. Tolerance levels. All right, so generally, we want to choose tolerance levels that are dialed in just right. We don't want them so tight that we get a lot of false positives. We're getting alerted to non-clinically relevant issues. So we're chasing down lots of alerts that don't really have much impact on the patient. We also don't want them so loose that we don't get alerted to things that are affecting the patient in a meaningful way. So it's important to maybe start with the recommended tolerances and then reevaluate over a course of time if they're working well for you. Briefly, some of the 2D, some of the tolerance levels that we discuss when it's relative 2D transit dosimetry, since you're not calculating absolute dose, kind of standard to pre-treatment QA, a very similar amount of tolerance is going to be achieved there. Absolute 2D, now you're calculating dose, and so it gets a little more complicated, a little more uncertain. So a little bit looser. You can see the recommendation there at the bottom. But it's more sensitive to dosimetric errors than the relative mode, as you would expect. 3D transit, where you're looking at the full three-dimensional dose, more complicated again. Lots of assumptions have to be made to get that three-dimensional dose. So your level of agreement is going to be less than 2D. And we have specific recommendations in the report. I didn't want to get into the specifics here because of time. DVH, building off of the 3D. DVH does all the same complexity and uncertainties with 3D, but now you also have all those contouring issues as well. So again, you have to be very careful what tolerances you do. But now, instead of gamma analysis, which you can do as well, you can start to do metrics like PTV coverage and are my OARs now failing their dose constraints. So these are much more powerful and much more clinically impactful metrics, right? And another recommendation is if you're right up against, say, a spinal cord dose, you might want to change your tolerance for that specific patient to make sure you don't exceed that, so you can dial it in specifically for certain situations. And I recommend you do that. And then just to finalize things, kind of nice summary, we have a risk-based analysis section of the task group report, and it comes away with some key messages. So there's some distinct advantages in detectability of certain failures as compared to pre-treatment QA. So you're going to see different things with transit dosimetry than pre-treatment. Doing first fraction transit compared to pre-treatment QA has been shown to show wrong isocenter, patient alignment, and error in CT scan data. Transit dosimetry for all fractions. You can now detect patient motion on the table, treatment machine errors, setup errors. And just know that your transit dosimetry choices, whether it's 2D, or 3D, or relative, or absolute, they greatly affect the kind of errors you're going to detect and the sensitivity of those detections. There's a ton of references in the task group report. Here are some key ones that I kind of mentioned specifically here in the talk. And I want to say thank you for your attention. I like the opportunity to present, and these are my co-authors of the task group.
Excellent. Thanks, Kyle. Okay, so before I introduce our last speaker, I'll remind everyone that we will have a Q&A panel discussion style session after the last speaker, and we have about a half hour dedicated to that, so please stick around. Our next speaker is Dr. Louis Archambault from University Laval in Quebec City. Louis is an expert on research and development of scintillation detectors for radiation dosimetry. And today he'll be talking about their use for in vivo dosimetry. So go ahead, Louis.
Thank you very much. Hi, everyone. So let's start with some disclosure. So I own some intellectual property that has been licensed to both standard imaging and medicine. And I have an ongoing funding in partnership with medicine. So my objective today is to present the first a rough overview of plastic scintillation detectors, summarize their strengths and weaknesses for in vivo dosimetry, and discuss how the current state of commercial options can be used for in vivo dosimetry. So compared to all the other speakers before me, plastic scintillation detectors are maybe the newest kid in town. It's not been tens of years that we've had these commercial options. So I'll talk about a bit about that, and then I want to go over some example of actual application of PSD for in vivo dosimetry. So let's just start with the basics. So a plastic scintillator, as its name says, it's a plastic. It's a mostly water equivalent material that will emit visible light in these really nice color that can go from blue to orange. When they are irradiated. And the idea behind these kind of detectors is to link the amount of light emitted to the absorbed dose in the detector. So just really, really briefly how it works. So there's the ionizing radiation will deposit those within the polymer matrix. And then energy will be transferred from the polymer matrix to a first fluorophore that will, this energy transfer happens non-radiatively, and then energy is again transferred to a second fluorophore that will emit light in the visible range. And that's that light is usually it can travel through the plastic because the plastic is transparent at these specific wavelength, and we go and measure it. So the anatomy of a basic, there are many shapes and forms, but ideally plastic scintillation detectors is composed of three components. So first we have the scintillator itself, the plastic I just mentioned. It is coupled usually to an optical fiber to carry the light up to a photodetector that can be anything from a photomultiplier tube or to a camera. So when we do irradiate this detector, the scintillation light will be emitted and will be transported through total internal reflection within the optical fiber up to the photodetector. One common problem with plastic scintillation detectors is that when you irradiate, you cannot just irradiate the scintillator itself, you also irradiate the optical fiber, so the stem, and that also generates some light. It can happen through Cherenkov radiation or fluorescence. And that has been a problem for many years for scintillation dosimetry. So what we get in terms of wavelength here is both the scintillation that you see in blue here and the Cherenkov and or fluorescence that you see in red here. So these two spectrum, what we are interested in is just the blue curve, but these two spectrum overlap, and it's impossible to filter just one. So if we cut, for example, with an optical filter, we will still get some Cherenkov and some scintillation, and what we want is scintillation itself. So many techniques have been developed over the years to decouple these two signals so that we can extract just the oscillation. The first technique originally developed by Sambada is the what I call the subtraction method. So you use two fiber, one fiber with a oscillator and one clear fiber with no oscillator attached. And then you give the same dose to these two devices and you subtract them to isolate the Cherenkov. So it's really simple process, but it does require that both the background fiber and the actual detector receive exactly the same dose for it to work. And then a bit later, there's been more like a spectral approach developed. So the first of these is the two waveband decoupling. So in that case, we measure the total signal. We have a single, just a single optical fiber with a oscillator attached. We measure light in two different wavebands. And then we can build basically a two equation, two unknown system to isolate the contribution from the oscillation. And a bit later, we developed a hyperspectral approach that instead of using just two wavebands, use tens or hundreds of wavebands. And that gives us more power. So we could consider more overlapping spectra. And that gives us technically a more powerful decoupling method, but it's also come at the cost of a more complex calibration procedure. And these three approaches have been implemented by different vendors. So Blue Physics has gone with the first method, Standard Imaging mainly on the second approach, and MedSynth with the third approach. So, so as I said, we can link with the amount of light produced in the oscillation detector to the dose absorbed in the sensitive volume. For high energy particle with relatively low LET, the light emission is proportional to the dose, which really make things simple for calibration. But high LET particle like protons or heavier ions will show some quenching. So there's a nonlinearity happening in the oscillation emission. And for years, we thought that was about it. So at clinical photons and electrons, there was no issues. But recent work by the group of Klaus Andersen in Denmark showed that some quenching, some nonlinearity in the emission can happen in clinical fields because of the low energy photons from scattered radiation. So when you have a larger field size, you have more scattered. That scatter has lower energy and can cause some quenching. So it's relatively small. We're talking about 0.6% difference between 0.5 cm field to a 10 cm field. So it's small, but it's there, and we can actually account for it and correct for it. So recently, MedSynth has put out a new oscillator that aim to balance the material response to the quenching, so that it provide a uniform response no matter what field size. So in this figure that you see here, from field size from I think 6 millimeter to 10 centimeter, you see that the output correction factor is really constant and really close to 1 for the oscillation detector, while all other detector show some variation. So we can account for these, but when we're talking about in vivo measurements, then we can have a treatment, an IMRT treatment or a VMAT treatment that use both large and small field, and we so it's good that the detector has a uniform response no matter what field size is used. So an overview of the other oscillator properties. So they can have high spatial resolution. So most vendor will offer you a detector with at least 0.5 millimeter resolution, but in theory, we could have much smaller sensor size than that. It is extremely fast. So the oscillation process itself is of the order of a few nanoseconds. And so the time resolution is usually limited by the photodetector itself. So it's good for online measurements. It is they are water equivalent. So both the mass attenuation coefficient and the stopping power are really close to that of water. which make really small perturbation. They have a really good angular response here, a plot showing the detector response as a function of beam angle, and we go from about at most 1.5% variation. So again, that's really useful for in vivo, because if you're treating a VMAT patient, then the beam will come from every angle, and it's good that you have no angular dependence. They are independent of dose rate, of pressure, and unlike ion chamber. They are compatible, although they have some signal dependence, but they are compatible with MR LINAC, and they are reusable. So, there are clear advantages of plastic simulator for in vivo application. They have a uniform response. They are accurate, and they are free of angular dependence, and they don't cause a significant perturbation because they are water equivalent. So if you have a 0.5 millimeter probe, it will cause at most 0.5 millimeter attenuation of the beam. And you can read them in real time. Some limitation of plastic simulators, they have been shown to be slightly dependent on the temperature. So it's not a problem for measurement and phantom, but if you're sticking them in or beside a patient, then it might have to be corrected for. You can do a correction specific, calibration specific at a given temperature to correct for that. And unlike TLD, OSL, or films, they do require a cable for readout, which is annoying. Although there's been a recent paper in Nature Biomedical Engineering that showed a prototype of a simulation detector that is fully wireless and that could get the readout from your cell phone. That looks extremely promising, but it's probably a few years from entering the clinic. So, so as I've mentioned, there are 3 companies making commercial plastic simulation detector. Standard Imaging were the first with the XRADIN 1, W1, and then a bit later XRADIN W2. MedSynth with the RP100 and RP200 platforms, and Blue Physics with Model 11. So the problem is that from these 3 companies, only, to my knowledge, only Standard Imaging has received FDA approval, although both other companies are actively working on getting FDA approval. But in all cases, none of these vendors have been specifically approved for in vivo measurement. And that means that whatever you'll see in the literature in terms of in vivo measurement will either be off-label use, preclinical research, or a clinical research protocol. So I'll show you an example of all these. So example of off-label use from our clinic, some example in preclinical research, and then some human protocols. So so in our clinic, we do use the XRADIN W1 once in a while for measuring pacemaker or cardiac implanted device. So we do an evaluation of the dose to these when we have patients with pacemakers. And if the dose is close to our tolerance or close to 1 grade, then we'll typically do an in vivo measurement for these. One case that struck me as pretty rare is a patient with a cardiac pump that we got a few months ago. So the patient had both a defibrillator and a cardiac pump, and the PTV was somewhere in between. So we needed to be really, really careful. So we did in vivo measurement with the simulator. So and the patient was actually treated with 2 arcs. We estimated from the TPS and NCalc to about 48 centigrade, which was safe, but we preferred to do in vivo just to make sure. And we did, and we found out that our calculation estimate was conservative, and that was gave us confidence that there was no risk for the patient. Some preclinical work. So we did a mice study for measuring skin damage. And so we had the idea to stick a simulation detector in between the bolus and the animal and monitor the dose in real time. And that's just 2 examples of what we get. And the nice thing about doing online measurements is that we can actually catch when an interlock or when an animal is moving or something like that. Another group has done a study on dog measurements. And what's interesting in that work is that they actually did a correction for temperature dependence of the sunlighter. And the measurements were quite good. So between 2 and 3% of the expected dose. And that is really encouraging. For brachytherapy, I'm really not an expert in brachy, but one advantage of stimulation detector with the hyperspectral approach is that we can stick multiple stimulation element on a single optical fiber. So when space is constrained, that's a good way to get it. And so we've shown that we can actually use these kind of device for tracking the brachytherapy source. So there's a big need for in vivo measurement and brachytherapy. And we also did, not me, but the group again of Sam Bedard in Houston, they did in vivo measurement by placing a stimulation detector on a rectal balloon. And what is impressive here is that you stick the detector really in the gradient region of the beam, and that's where you want to measure the dose. That's where uncertainty is important, that you want to see if the beam overshoot or undershoot, and that's a good way to do it. And the precision was pretty accurate. So just to conclude, I'm biased, of course, but I think that stimulation detector has a lot of potential for in vivo dosimetry, and I think that we'll hear more and more in vivo application with stimulation dosimetry in the coming future. They are accurate, they have uniform response, and so we've seen some example in the literature. And they have a few limitations, so some temperature dependence, they are not yet wireless, but I still think they could work. Thank you very much. And if you have any question, I'll be happy to take them.
Okay, great. Thanks, Louis. I'd like to thank all the speakers again. We have several questions in the Q&A box that we'll start going through. Some of them have already been answered by the speakers. We will go through the ones that have already been answered in the text and review those. But I'll start with the questions that have not been answered already. The first question is, what OSLDs are you using since Landauer's recent recall? And I think this is directed to Paula, but all speakers can chime in after Paula finishes.
So I think I addressed this question with other comments that came up later. Right now, we are still using OSLDs, and the reason why we are using is because we have a conversation with our legal department. So, and that's why I made that comment very specific. And right now, we are completing the commissioning of the My OSL chip from RadPro, which is an OSL system also, but based on beryllium oxide.
Are any of the other panelists still using OSLs?
Maybe I can speak a little bit of that too. We also still using an OSL system, and in combination of films and bleaching and the whole thing. But I have to say, we do spend a lot of time taking care of the system, which it may not be feasible for a lot of places. So just a caveat, I also bug Paula also in terms of we're also looking into my OSL also. Yeah, it depends on the workload of everyone. So.
Yep. I'll also say that so there have been a couple questions about reusing and bleaching OSLs and things like that. We will come back to those questions, but reusing OSLs from nanodots from Landauer, that's something that should probably be discussed with leadership and be carefully considered. The recall notice did say that unused dosimeters should be sent back to Landauer and used ones should be destroyed. So, if you're using them, make sure that you're getting accurate results. There's TG192, which gives guidance, but certainly think about legal implications and discuss with your leadership, things like that. Okay, the next question, I believe this is for Patty. think you may have mentioned Cherenkov imaging during the intro talk. Why introduce Cherenkov imaging as it is being investigated for dosimetry?
Mostly, I just brought that up as an example of an emerging technology. That's all.
Yep, sounds good. Okay, the next question, the Landauer MicroStar 2 system was reasonably priced for a small department compared to a TLD Harshaw system. With the removal of this system from the market, is anyone aware of reasonably priced systems that would replace the Landauer MicroStar 2?
I'll take that question. There are detectors or systems that similar to that are at the same level of price. But I would make the biggest recommendation of understanding the difference between the system you're taking and compare how you were using the OSLDs. So in our case, weight has been regarding the geometry, how we set the detectors in place. And so the decision needs to be more not only based on price, but only how the implication of the change you're going to make. And so again, we decided for the RadPro system, but when you're looking into that, you need to look for the change that the new system is going to imply on the department. And is that change not necessarily means the price of the detectors. It's everything else you have to change, like software, calculation of those, phantoms to set up that. Those type of things might make also an impact in the final price.
So back to bleaching and reusing. OSL's Joanna Sigler had a comment that you can easily make your own bleaching box with standard incandescent bulbs. There's a paper on this from Amatoyo called The Effect of Different Bleaching Wavelengths on the Sensitivity of Aluminum Oxide Detectors exposed to 6 MV photon beams. So if you're interested, have a look at this paper. The next question, is anyone in or out of favor of diodes and why?
I can say a little bit more because I think our department still use diode for a certain type of in-vivo dosimetry. It is really a preference, I guess, in my mind, of the physicists, if that is something they're willing to use. And one of the concerns from my perspective, it's all the cabling and wiring that comes with it when it comes to in-vivo dosimetry, and some of the therapists may not be too keen on that. But it's nothing really against it per se. It just like any detector, you just need to be mindful of the pros and cons of
that. Wes, I think you also had something about MOSFETs and diodes, if you wanted to summarize that.
Yeah, someone else had asked a question, so I typed in the chat. Both in the center, and actually I think they're both viable options. They both involve some cabling. The mobile MOSFET system is made to mount to the couch, so the cables are a little shorter. I feel like the diode system was a bit more robust and accurate, and you don't have to throw them away. The MOSFETs only have a limited lifespan of 20 gray or so, and then you have to get rid of them. So you have to calibrate each new set of MOSFETs. I thought that was a little laborious. It does hold up to 5, so that like Gary was saying, it's kind of some pros and cons. If you do TBI, you might prefer something like a mobile MOSFET system. The diodes tend to come with different amounts of buildup on them for different energies. So you end up having 3 of them or maybe 5 of them hanging in the corner of the room, which is nice because they hold their calibrations well. But it's also a little harder to put them under some bolus and a little clunkier. I'd say the accuracy, in my experience of the diodes, is much higher than the MOSFETs.
Thanks. This one is for Louis. So Louis, can you talk about any experience using scintillation detectors for proton or carbon ion beams?
Yeah, we've used them in the past with protons. Again, the quenching effect I mentioned is much more important. There are between the plateau region and the Bragg peak, there can be several, possibly 25% drop in signal linearity. So if it's modeled accurately, then you could use them for protons. For carbons and everything heavier, it's probably even worse. So that might be more difficult. But for proton, they're definitely usable with the proper calibration.
The next question was for me. Any reason why MOSFETs were not covered? Many clinics, including ours, use these detectors. Apart from external beam, they can also be used for brachy. So no, I don't really have any comments. As we were going through this with WGRD, people gave me different suggestions to include in the proposals. No one brought up MOSFETs. That's probably just because on our working group, people weren't using them. So yeah, now is a good time to talk about them. If anybody else has experience, I know Wes touched on them a little bit, but if any of the other panelists have any experience with MOSFETs, please let us know. Yeah, it wasn't intentionally that MOSFETs were left off. So. Okay, so maybe that can be part of a future webinar. What are the implications of clinics using devices off-label, so not FDA approved? Are there legal issues if there is a problem? Can we not bill if the device is not FDA approved?
I can just for that. I know in our clinic we did use them off label, but we were backed by end calculation. If the measurement were actually came higher than the calculation, then we would have to think a bit more about what we did. The physicists did that to just essentially for themselves, and being in Canada, we don't bill for it, so it wasn't an issue for us. So it just to increase confidence. But if you are really interested in doing that legally, then you can actually, within the scope of a research protocol, we can ask a derogation to, for example, Health Canada in Canada to do these kind of trial. And we've done it with for the brachy, for example, we actually did it properly like
that. Anyone else at an American clinic know anything about using non-FDA approved devices? I'm assuming there are allowances for research purposes.
It really depends on the application. If it is really day-to-day clinical operation, I think in that case, or billing issue, then they really need to talk to the compliance office and as well the billing department, exactly what is the scope of that and how much liability is the hospital is willing to assume if you want to do something that is not FDA approved. So it really depends on the institution, in my mind. Yeah.
Great, thanks. Okay, so Joanna had another comment. One should always do the calibration in the clinic and not rely on the manufacturer. This goes for OSLs like nanodots. The next question is for Kyle. Kyle, do you feel EPID transit beam dosimetry is becoming more popular here in the US? It seems to be very well used in Europe.
Sorry, I muted again. Yeah, I don't have any specific statistics or guidance on like how heavily it's utilized and how that's progressing over time, but it is growing. It is seemed to be adopted by more and more clinics. I see presentations of this technology at more and more meetings and more case studies being presented. So I do think its adoption is in the positive direction, but I don't have a handle on how much.
And the next question is also for you, Kyle. So have you noticed increased failure rates with EPID detectors for highly modulated plans, or is it mostly due to detector calibration?
I would say they're both a source of error when it comes to having things fail. Highly modulated plans, if you have your TPS, if it's not modeling the leakage extremely well, then you're going to have, for highly modulated planes, you're going to have an increased error rate on things like patient-specific QA. It's going to translate to transit dosimetry as well. I would say the patient-related things would dominate transit, though. Like if you have patients changing in weight or bowel gas, that stuff will probably dominate over highly modulation-induced errors. And then the dose calibration is something that you have to stay on top of. If you monitor it on a regular basis and you correct for it when it gets out of tolerance, it should not be a significant source of error in your measurements. But if you aren't doing the measurements often enough, they can get further out of line and actually cause some issues.
The next question, do we know the root cause of the recall? I don't think we do. It's probably best to just contact Landauer directly for that one. Is Adaptivo and EPID system the same?
That's for me, I'm sure. Well, the EPID is the NV detection panel that's attached to your Linac that pops out and sits under the couch for like an AP beam, and collects the radiation dose as it exits the patient. So EPID stands for electronic portal imaging device. And Adaptivo is not a software package that I have personal experience with, but it's I think a standard imaging solution where it takes this data collected by the EPID and will reconstruct it in 3 dimensions and do a lot of the functions that I talked about in the actual talk. So it's more of a solution. So it uses the EPID, but it's not an EPID itself.
Thanks. Paula or others, have you had to adapt existing phantoms to fit different models of OSLs or TLDs in lieu of nanodots? Can you please speak about your experience?
So the original system was everything based on TLDs, and the TLDs that we are using is not the same as was presented. We are using powder. So the reading technique is a little bit different. Anthropomorphic phantom are still using TLDs, while an output check, we decided to move to the OSLDs, and so all the mini phantoms were redesigned. But after that, we have not changed detectors, so all the adjustments or all the things that we are developing are based on these 2 models.
Anyone else have experience modifying or adapting phantoms for the devices they're using instead of OSLDs? Yeah. We've done some type of work with this on different applications, like basically making inserts to fit in existing phantoms and things like that. So it can be done if you have especially if you have a good machine shop, then they can adapt things. But diodes also have a limited lifespan, but they are longer than MOSFETs. Okay, this is probably for Gary. How about using radiochromic films for in vivo dosimetry as a replacement of the OSLD?
For high dose application or in-field dose application, we're using film at this point. But for low dose, as shown in the presentation, we do have high uncertainty, especially for our field dose, anything less than 40 centimeter or 0.4 gray. So we're still relying on other detectors such as OSLD. We're using OSLD or MOSFET or diode. So we basically have a different portfolio of things to replace current OSLD or reuse some of the old OSLD. To answer the question.
Yep, that's good. Louis, are there large variations in scintillator signal based on the length of the irradiation of fiber optic cables?
Yes, because of the stem signal, the raw signal will vary greatly with the amount of fiber irradiated. But if it is properly calibrated, the measurement, the dose signal that you get out of it will be pretty stable no matter how much fiber get irradiated. I would say at least you shouldn't see more than a 0.1% variation of dose signal if no matter how much clear fiber is irradiated.
There are also techniques to account for the irradiation of the cables. Question for Gary, is MSK using EBT film for in vivo measurements usually done for their TLD, OSLE, LD, or diode?
We only use it for high dose measurement, as I mentioned earlier on. For in-field measurements or 2D, we'll use the EBT film right now.
Kyle, would you be able to touch on more limitations of using EPID for absolute dosimetry, especially for small fields such as SRS, IMRT, QA?
Yeah, good. No, EPID dosimetry is useful for doing absolute dose calculations in a various amount of situations. The accuracy of that dose calculation depends on what techniques and what applications you're doing. Small fields are one of those areas where the accuracy is diminished and the uncertainties increase. I'm not an expert in that area. I don't use it specifically for SRS transit dosimetry solutions, but the amount of scatter gets hard to model, and some other aspects of small field size can be challenging. I know the EPIDs have a pretty reasonably good resolution, but if you're talking about really small field size, you will get a response, but your ability to resolve that properly can be challenging, and any small deviation in MLC positioning and the modeling of that is going to be challenging on your EPID as well. So I don't have a specific reference to recommend, but I bet there's one out there that takes on this exact topic on what's the limit for absolute dosimetry for SRS dose calculations. It may be a pre-treatment QA paper, but have similar applications to transit dosimetry.
Just want to add on to, I think, to what mentioned earlier on, and it really depends on the beam model and what kind of software you have, because I think there is certain limitation in terms of non-water equivalent scatter behavior with, let's say, the variant model vis-a-vis some other commercial system. So your mileage will vary, and it depends on exactly how you commission your system as well. So just be careful with that. For my institution, we use it for SRS, but we do have special beam model specifically for that, and we spend all the time commissioning. So, but it's not also compliant with TG218, so something you might want to think about too.
Thank you, Gary.
There have been a few general questions about can the slides be made available after the webinar and if the webinar will be recorded. So the webinar is recorded by AAPM. It'll be posted online on the AAPM website after the webinar. So I'll get back to specific questions. This is for Gary. Is EBT4 more sensitive to the position on the scanner than EBT3 film?
I don't see any big difference between the two films, but I do realize, well, noticed for the EBT3 in the past few years has some batch-to-batch variation issue in terms of uniformity. When it comes to scanning, I think I also answered another question previously. I just want to also reiterate the placement on the film on the scanner is important because the scanner has a non-uniform behavior at times, and there's well-documented lateral issues. So one has to be careful about, especially when you do 2D and you want to be consistent when you scan. And the second of all is the polarization issue of film, radiochromic film. Doesn't matter EBT 1, 2, 3, or 4. You want to make sure you scan it consistently in the same orientation so then your grain of your polymer is the same orientation, so you don't introducing unnecessary uncertainty in your film reading.
The next one is also for Gary. You mentioned observing higher uncertainty in lower dose measurements with EBT4. Have you evaluated this with films designed for lower energy, like films specifically used for medical imaging?
We have not. And I also worry about I think my understanding is there are some high Z material put into the medical imaging films. So we are sticking with, tissue equivalent films. That's a very good question.
Thanks. The next one's for Kyle. Kyle, do you have recommendations for different EPID software solutions on the market, or where one could find good comparisons? Have you demoed many different solutions personally?
So I don't want to give any specific recommendations. I have demoed a couple of these different versions at my own clinic, as well as at various meetings. There are a lot of really good solutions out there, at least as far as the demos that I've received are. So I recommend you look on the task group report that we published. It's got a table that summarizes all the different solutions that were currently released at the time of publication, which is under a year ago, about a year ago. So it's pretty up to date. So you can see a list there. And it also gives the details of what the different solutions are, whether they're 0D, 2D, 3D, DVH, and then also goes into some of the algorithms and different choices these vendors have made. So I recommend starting there.
Math resolution is a commercial solution that uses EPID for transit dosimetry. What about new systems coming up with larger capabilities? My concern is dose reconstruction. Is it going to improve the methodology?
I don't see that one. I didn't read it. Could you repeat that? Oh, no, I see it now. Is it going to improve? There's no reason to believe that the dose reconstruction wouldn't continue to improve over time. I'm not familiar with a specific product by Math Resolution. I'm probably just going to have to pass on that question unless somebody else on the panel knows more.
Yeah, fair enough. Okay, is there signal decay of OSL with time? If we read the same irradiated OSL multiple times, do you get the same reading?
I'll take that. So yes, there is a decay, which is characterized as depletion in the process of reading and fading in the way of how much time you take from irradiation to read them. So those two factors are presented in task group 191. Regarding reading multiple times, I want to make a very strong comment about that. The reader might not be stable. So even if the detector is going to show the same thing every time you turn on the reader again, the PMT and the whole electronic configuration might change. So assuming that you're going to just put the same detector and it's just depletion, what I'm using, how many times I read it, or fading, and turn on, put the detector and start reading, nothing guaranteed that it's going to be the same signal. So on the case of OSLDs, you always need to use something that is going to calibrate your detector. Any kind of reference that you use that is going to be read at the same time of your detectors and is going to provide you the calibration of the system.
Thanks. Gary, would you elaborate on uncertainty contributors to low dose film measurements? Is it possible to improve this with better film calibration, for example?
I think it's really, if you look at the Devitt curve I show in the presentation, is really hitting the physical limit of the uncertainty of the film itself. The reading and calibration is pretty much stable across all dose range. It's really the signal to noise when in the low dose region, when your measurement dose is so close to the base fog. So you're really hitting the limitation of the film. So I don't think this is something, we can just calibrate it out.
Okay. For SBRT SRS treatments, where the dose may be greater than the range of the specified range of the films, we use EBT XD film, especially for small fields. Do you have any experience with this model?
XD film is actually our standard for anything high dose or single fraction or end-to-end test in that matter. I have very good experience with that.
Okay, math, this is just a comment. Math Resolutions is the original manufacturer of dosimetry check, which has been refined and implemented by the new vendor. Could we use film smoothing and then use it for low dose? That could help with the noise.
Again, I think it's really the physical limitation of the film, the signal to noise. I don't think smoothing can fix signal to noise issue.
I think this will be the last question. We only have 1 minute left. Wes, can you comment on the precision of MOSFETs?
Okay. Probably not commenting too well. The last experience I had was about 10 years ago with the MOSFETs, but I thought the precision was actually quite a bit higher than 5%. This is when you place it on a Phantom and I reiterated it 3 or 4 times in a row, I would get variations up to 10%. That was with the Best Medical mobile MOSFET system about 10 years ago. That's my recollection.
I don't think it has changed, Wesley. I just got one, and it's the same behavior.
Okay. It's unfortunate because there is a lot about that system to like, but I did not have a lot of confidence in the
I agree. I have
repeatability.
the same problem. Yeah.
Okay.
Okay, good. So yeah, so I would like to thank all the speakers again. I think it was a very useful webinar. There were a lot of general comments in the Q&A saying thanks to the speakers. It was a good webinar. So yeah, I'd also like to thank all the participants for attending and for your great great questions that helped us stimulate good discussion here. And with that, we will end the webinar. Thanks.
Thank you, Brian, for organizing.
Thanks, everyone.